Yes, thank you, Christian, and thank you everybody for coming. What I will present is really a joint work with Christian at the TLK Thermo and Manuel Graber at TLK Energy, and my colleagues Elmir and Dag and Julius at University of Augsburg and Oliver at Bosch. So, what I will present is basically two new technologies to speed up co-simulation, and they have been implemented in inDymola. And yeah, the target is to speed up co-simulation, and the idea is that it should be easy to use, but at the same time somewhat widely usable. So this is kind of the target. I'm not saying that we succeeded with this, but yeah, this is what we are aiming for. And the target user is anyone who wants to export some heavy co-simulation FMU from inDymola. So with heavy, I mean that it takes a lot of time to simulate it, the FMU. So I will just shortly go through the two techniques. So it's input smoothing and it's predictor compensation, and then I will have a little bit wider discussion. So the idea of input smoother is rather simple. The normal co-simulation, normal way to do co-simulation is that you have this gray input to the FMU, and you have communication points. These are the crosses, and at each communication point, you sample the input signal, and then you hold it, and then you sample it again, and you hold it. Okay, so the input smoother done like this, which is an idea by Christian Schulze from TLK Thermo, is to kind of delay the input signal and do, so it's really the yellow curve. So you delay the input signal, and you can then ramp up to the new value. So instead of setting the new value immediately, you delay it, and then you ramp up to it. And in this way, you get a continuous input signal. So the yellow line is what the integrator inside the co-simulation FMU sees. So what's the purpose of this? The idea is, if we have a continuous signal inside the co-simulation FMU, that is better for the numerical solver. It means, for example, that we can continue integration over communication points. Possibly, we can do that. Because these jumps, you cannot continue integration over these jumps. You have to restart the solver, but with the input smoothing, you can continue. And the way it's done now in inDymola is that you just set a flag, and then you export an FMU with co-simulation. Then everything is embedded inside the FMU. This means no model manipulation, no special co-simulation master. The idea is to make it as easy as possible. So you just have this FMU, and now you take whatever master you want. And then we have another extra feature, which is called predictor compensation. So when you continue integration with, for example, Dussel or Sevode, over the communication points, it's not that easy to see maybe, but there are small knees in the yellow line, so discontinuous derivatives. That is still not very nice to Sevode or Dussel. They don't really like that, especially when they integrate with higher order. So if you have order 5 and you have discontinuous derivatives in the input, that's not good. You can remedy a bit, alleviate the situation, and you can do that with predictor compensation. So how this works is really that when Sevode takes an internal time step, they first make a prediction. So that would be the yellow line, for example, and then they make a correction. This is the Newton solution. And you end up at the solution, and that is the actual time step. If you have bad predictors, it will be difficult for Newton, because Newton wants the prediction as a start guess. And you can do predictor compensation, and you can come up with a better predictor, and that now helps Newton. It also helps with error control, because the error control in Sivode, Dussel, IDA, is all based on the difference between the predictor and the compensator. No, predictor and correction, yes. How it's done in inDymola is that we look at the knees in input, and we kind of make a directional derivative to see how it affects the state derivatives, or actually second state derivative. And we get a better predictor. And usually it is much, much better like so. This is from an actual example, and I had to dig to actually find something that I can present, because all of the case, it was always exactly on the gray line. So yeah, this is the worst case I could find. Just a simple example to show how this works. Yes, this is a mass spring FMU. No, this is a mass spring model split into two FMUs. And they are co-simulated. Only the mass FMU has states, so position and velocity. And in the mass FMU, we might use inputsmoothing and predictor compensation. And we have some statistics here for different solvers. And with a classical co-simulation, we have to restart the solver at each communication point. This means re-evaluating the Jacobian, for example. So we have 500 communication points. That means 500 Jacobian evaluations. By just smoothing the input, we can reduce that to 40, and also less F evaluations. If we also add predictor compensation to help the integrator, we can reduce the number of Jacobian evaluations even further, and also the number of function evaluations. The cost is, of course, there is some cost, because we have to approximate the directional derivative. So there is some extra cost, but yeah, it pays off in this case. Now, so the problem is, maybe I was a bit fast skipping forward, but you have the correct solution here, and this is really exaggerated to be a difficult problem where you have a lot of oscillations. The blue line is the solution from normal co-simulation, classical co-simulation. The yellow line is with using inputsmoothing. And as you can see, the oscillations, the numerical instability is worse, which is, I guess, expected when you add additional delays, which we do with inputsmoothing. Which gives us this discussion here. So I really want to emphasize the idea with these technologies, or these two technologies, is to speed up. It's an efficiency idea. It is not a general solution for all your FMI co-simulation problems. It actually makes stability worse. And if you use and try these things, you need to be aware of that. But it can speed up the simulation a lot, and I will show that. It is, of course, a well-known idea to do inputsmoothing, and there's everywhere in the literature, not only when it comes to FMI. I think the novelty here might be that it's very simple. It's all done inside the FMU with no special model manipulations, no special co-simulation master. That's certainly a benefit. It's also a negative part, because it's just mathematical. It's not physical. So you have something like transmission line modeling, where you have physically motivated delays, and then you get also efficient co-simulation, but more physically motivated. But again, the idea is to make it easy to use. And we've found we have got some feedback from people trying this, and I think where it's usually very useful is, first of all, the exported FMU has to be computationally heavy. If it's very easy to solve the FMU, it doesn't really make any difference. Communication interval should be small, and stability shouldn't be a big issue. One particular use case is real-time simulations, where you usually have a very small communication interval, and it is kept small, not for stability reasons, not for accuracy reasons, but really due to real-time requirements. And this is one use case where we have seen orders of magnitude speed up. So, a first example is this heat pump based on the TIL suite. So this is from TLK Thermo. It is used for hardware in the loop simulation, and therefore it has a fixed communication interval. It has a noisy input. And in the paper, Christian made 17,000 simulations. So if you want to see more details, you can look in the paper, because there's quite a lot of information there. The setup is really simple. The whole FMU is exported, and there's only one input, the valve opening area. And this valve opening area has some noise. And we have quite a lot of results, as I said. So we have different use cases. We could, for example, look at this one here. I don't know how to point. Yeah, the middle one on the third column here. So this is a use case where we have a high resolution. This means that the spatial discretization is quite detailed. I think it's something like 400 states. And what we can see is the speed up factor from using inputsmoothing with or without predictor compensation. The sharp blue line in the bottom, this is the base case, the classical co-simulation. And the speed up factor for inputsmoothing goes all the way up to about 400 times faster when you have 10,000 do steps. So 400 times faster in this case, and it's similar in other cases as well. We can see the red line. This is predictor compensation. Predictor compensation, it doesn't really help when we have 10,000 do steps. But it does help a lot, somewhere in the middle, around 200 do steps. It helps a lot over just using inputsmoothing. So this is the case where all of these knees in the inputs really is bad for the integrator. So helping it makes a huge difference. And we also have some results to show that the result changes a bit, which is natural because we do the delays, but it generally follows the same curve. We have the second model as well, this time from Julius Aka, and it's also it's a refrigeration cycle. It's much more detailed. It comes from Bosch and used in the OpenSCALING project. And it's used to generate data for training surrogate models. So inputsmoothing comes in as a way to speed up the data generation. It's the heat pump with the controller exported to FMU. It has two different operating points. Either you have controllers that are tuned and kind of give a nice simulation, or you have high gain controllers that make the simulation a bit crazy. And we did also some experiments with that. And I think the last column is the most important one, where you can see in the low oscillation case, inputsmoothing gives 40 times faster simulation compared to classical. Predictor compensation in this case doesn't help. When you have high oscillations, inputsmoothing gives some speed up. Predictor compensation gives a little bit more speed up. But due to the difficulty of simulation, what is done at the communication points doesn't really impact so much because, yeah, the simulation is very difficult. Simulating directly in Modelica is always better, of course. So final slide. I'm actually a bit early here. So there are two new features. They are enabled by flags in inDymola, of course. It's embedded in exported FMUs. There is no requirement to use special master. There are no requirements to modify your models. You can just set the flags and try it and see how it works. It does not solve all co-simulation problems. So you need to look what happens, especially when it comes to stability. And we have seen 10 times faster and sometimes over 100 times faster co-simulation. So for Dussel, it goes up to 400, the best case we measured. And and the next step would be to dive deeper into what happens when you really connect them and look more at the result and what happens more if you have several co-simulation FMUs using inputsmoothing and how much does it affect the result and things like this. Please set the advanced flags and try it out. I think I finished 1 minute early, actually.